Our focus in these lessons today is about exponential functions and models. And our targets are to be able to identify in an exponential function the variables that are provided and what they represent, the domain and the range of those functions. We also want to be able to describe properties of exponential functions, find the equations for data that is exponential, and interpret those exponential function parts, graph them, and then interpret properties of relations from graphs. We'll finally be using scatter plots, and these are not necessarily done in the order in which I provided them here, but using scatter plots that relate to real-world data that we can use to draw conclusions about the data. And most of the data, of course, that we'll be looking at will be exponential. So when I make these videos on my iPad, often the math type functions don't come through very well. So this function, f of x, is actually a times b to the x power. That's an example of an exponential function. X, the exponent, always represents the number of time periods. So what is it multiplying by every period of time? And y represents the value of whatever it is we're measuring after that many periods of time. A is always the beginning amount. So the beginning amount will always be this number out in front of that power. Okay? So it will always be the y-intercept on the graph. B is always the amount by which it's growing. So in this case, it's being multiplied by b, and if b is a number greater than 1, it's going to get bigger and bigger and bigger over time. If rather b is a number less than 1, it's going to get smaller and smaller and smaller over time. So in any exponential function, y equals a times b to the x power, a, the number out in front, is the beginning amount, and b, the base of the power, is always the amount by which it's multiplying by, which is called the growth factor. If b is bigger than 1, it will get bigger and bigger over time. If b is between 0 and 1, it will get smaller and smaller over time. So here's a basic example as it relates to real world situation where the data is exponential. Y equals a times b to the x power. Let's say that we know that a particular species of bacteria grows at a rate of 20%. Now 20%, when expressed as a decimal, we know would be equal to 0.20, because any percent changed to a decimal, you do so by moving the decimal point 2 places to the left. But if b was 0.20, this would be an example of exponential decay, because that's a number between 0 and 1. Well, this isn't decay. This is a situation where the bacteria is increasing over time. So you have to consider the fact that the bacteria begins with its initial starting amount, 100% of the initial starting amount. Then an additional 20% is added after each period of time, in this case 3 hours. So we're really dealing with a situation where our growth factor is 120%. And when you express that as a decimal, moving the decimal point 2 places to the left, that gives us a growth factor of 1.20, which we mentioned previously will be the base of that power. A is always the starting amount. So the starting amount of bacteria in this case is 1,000. So A in our situation will be 1,000. So when writing an exponential function that relates to this real situation, our equation would be y is equal to 1,000 times 1.20 to the x power. And we want to remember that x represents the number of periods of time that have gone by. So x is the number of 3-hour blocks of time.